insider secrets about the general landscape of students at U of L. So the university gives the student government, just everybody, $1.3 million for general purposes. And guess how much of that money goes to graduate students?
Zero.
$3,000.
$3,000.
More than that. It's like 40.
40,000?
Yeah.
Okay.
Out of that large sum. Kyle, sir, I have a whole bunch of.
I saw
you
that.
did. Did I do a good job?
Yeah, I didn't dig into it much because I was on the way here, but I was like, holy cow.
I know. Yeah, so I got some boxes. I'll need some help, but you want to meet tomorrow? We can carry that over to Hutchins together. But in that big red bag, there's little goodie bags with the candies and stuff.
Cool.
Keep it simple. I've gotten 2 emails from people sad about the
About homework.
socks and samosas.
All right. Did you cancel? Did I miss that?
Yeah, well,
I'm sorry.
I didn't make a big deal
I
about
saw
it.
his hand go from steady to shaking at
But
that time.
Yeah, I'm like, I've done nothing
Well,
but
she got
for the
COVID.
past week.
Yeah.
yeah, so
I remember he
I'm like,
mentioned that
well,
you
I
used
didn't
the
have any,
matrix, but you couldn't
like,
get 0.
Yeah.
extra
Yeah, it
time
was-
or
I mean, this takes time, but
availability
fine.
to
If you
put
think
this together.
that is
Did I
okay, I
miss
just
that? Was it-
see that's
No, she just
some
emailed
mistake,
me.
but the
Oh,
others.
so
I
just
didn't-
nobody was
I
there
mean, yeah,
and
no
people
problem.
showed up, or? Okay.
So people were texting me like, "Oh, I went
I
to the
didn't
wrong
see
place."
that.
I'm
That's
like,
fine.
"No,
You want
sorry,
same
got
color,
cancer
so I
because
can
of
see.
COVID." So I kind of feel bad, but
I was like, I wasn't aware that was a thing.
is this the?
Yeah,
Homework
homework.
pile.
Is it
Next.
just me or is that first question?
Okay, so I
supposed
literally,
to be
I did
like
the
that?
same thing, and I'm like, this can't be right. That's way too easy.
Huh?
The dot product is just a number, right?
Yeah, exactly. That's what I said. The dot product's just a number, so it's commutative.
Oh, okay. It only not only show. It's just ask the community. I don't know what is the question.
It just asks you to calculate that commutator.
So that is number 6, right?
Because I did the exact same thing as
You're
you, Zane, and I swear to
overachiever.
God, I thought I was going insane.
In my case, I used that magnetic field is when applied in x direction, and I get the y direction and z direction.
Good job, good job. Let me see here.
I didn't
Hamiltonian
It's
is
still
the
true.
Simplify it all the way
direction
down.
of the
I
function.
simplified it to its simplest
Yeah.
commutative term,
Yeah.
which I knew it's gonna end up being 0 probably, but I thought that's what they were going for.
Well, I know, right, text says that the commutator of spin with any positional,
Wait a moment. This is not x square. It is s vector, right?
right.
Yeah.
So there's 3 components.
3 component. Yeah. I
And
have
then
it.
you have 3 components. Each component they do not commute each other. Sx does not commute with sy.
3 component.
Yeah, you have to go 3.
She did it right.
Yeah, that is correct.
I think I made a
Yeah.
I made a good.
Is this what you're looking for? I simplified it down to its simplest commutator.
Well, the rest of it just failed this class.
But this one, even though it's number, but it is.
At the first I was confused. Yeah.
You know what? That makes more sense.
Oh, literally, I think I literally put a note on mine. I'm like, I don't think this is right, but this is what I have.
So
Kyle, I'll write down all.
you
my
have
notes.
you have xx. Actually, xx is I and y h j yes, that is each term you have to do that.
Oops.
But Dr. Yu, that seems like more work.
Yeah. See how many piece work here.
Yeah.
Okay. I will count your effort. Give you credit.
50%.
Yeah. But you know, so I will not give you know what the difference, right? I mean the answer. So I will not give you answer, or maybe you can write answer on, or at least I can write this on your part of your question. You know.
I do have a question though.
Yes.
If I were to carry out this, like doing this simplification and carry out just this, would I still end up with the right answer, or is this cutting to here flawed?
This is vector, right? This vector. So you have actually, this vector you have 3 parts.
Yes.
So you have 3, not 1. You cannot take this one. You assume S is values, right?
No, I can.
So how can you?
I assume it's a vector.
Okay, if assume that's vector,
But then
I
this
use commutator algebra.
This
So-
one wouldn't be 0.
Okay, I
Right.
guess that one
Yeah.
would be 0. Okay,
Right.
so other than that, this part right here is still correct, and I'd have to follow through with it. Okay, good.
yeah.
Oh,
Okay,
my,
fine.
my fate is sealed.
That is last. In the final exam, you will not have mistake. That's why I ask you to do homework.
Right, right.
Yes.
That's good, that's good.
Okay. Let's do more exercises today.
We're learning.
Yeah, we
We already did.
I'm also
That's why
confused.
you probably discuss each other.
I should have discussed with Rishi.
Yeah.
Right?
Yes.
I was like, no way.
That's so simple,
I
right?
did not just do it.
I was grateful. I'm like, this is great. Moving on to the next one.
That is our the angular momentum different with others.
Kyle,
Okay.
we should have worked the
I
commentators
think
and PLCs.
we are done, right? So now let's do
Well, this one was easy. We just said, yeah, it looks like 0 to me.
the example which we
That's how I got a question
discussed
about
is
mathematical
orbital
correct.
angular momentum.
I looked at this and I was like, this looks like it's infinity. And, and after all the work, I got down to it, it was infinity. And I was like,
Pages later. Oh, it's 0.
Once had a professor tell me if you're doing E&M and you don't know the answer, just put 0 and you're probably right.
It's 0 or
Yeah.
You don't know anything, right, Zero? That's good.
Okay. So this is the wave function gave us. And the question, there are several questions. Let's see first. First question is, how about this? The L square, LZ, apply this wave function. And then ask us, what is the expectation value of L square? Actually, that is what is angular momentum? When you ask angular momentum means expectation value of L square take the square root. So that is the first question. Okay, how to do that? First, if you look this one, we do not know it is the eigenstates of this L square or LZ or linear combination of eigenstates, right? Since this is in the Cartesian expression or the Cartesian coordinates, so we know this one, right? Let's just remind you here. L square is a spherical harmonic. It is the eigenstate of L square and LZ, right? We know this. We also know this. This is also eigenstates of LZ. Erase. Is it okay? Okay, fine. So that is we know. But now we do not know this wave function is this or linear combination, right? So our first job is try to find the relation between the Cartesian or transformation between Cartesian coordinates and spherical coordinates. That we take the table. Look, right? So look at the table in chapter 5, right? 5.2. Oh, 5.3. Maybe 2, yes, I think. The first one is associated Legendre transformation and the polynomial. And then, yes, 2. Okay, look this one. So now I give you some of this here. We do not know it's the reason why I just look this y equal to 2 is because that will go to, so not y00 or y101 plus minus 1. It will not look this, so that is, you look at the table. So immediately go to the equal 2, so this one we know is, okay, xyz. It's xyz. In the Cartesian coordinates, we know this one is square root 5 over 16 pi 3z square minus r square over r square. Then the y2 plus minus 1 x, y, z. Why you may ask why I select this 3? That is, you look at the table, you know that only relate to this. So which one you are going to select, you are going to look at the table, right? And look this the Cartesian coordinates expression, then you can find the relation, which one is continuous. So this 2 and plus minus 1 is minus plus square root 15 over 8 pi. X plus r1 z over r squared. So now you look here. Of course, here is 2z squared, not and also x squared, y squared, right? Not this one. And this is not only xz, no y, right? So we need to rewrite this one such that it contains this. So because it's so, we are going to rewrite the psi x, y, z. Now 1 over 4 square pi. Here I put here. So now this one, I'm going to write down 3z square minus x square minus y square minus z square, right? I add one more z square, so I need a minus this one, right? Okay. And the second term I'm going to rewrite is 3 over pi r squared. So now here, x plus iy and the minus x, sorry. Wait a moment. Yeah, half. See here. Oh, wait a moment, I have one. Yes. So x, this is x, right? But if I use half, the x half, yes. So 2x divided by 2 is still x, is this one, right? Then I add iy and minus iy. So that's equivalent. Okay. Then now, the first term, you will see here. This is this first one, right? This is z, this is r, right? So that is 3z squared minus r squared, right? This x squared plus y squared plus z squared, right? So that is this one. And the second one, that's here. Second one is equal to, so I have a half inside, right? Inside is the r squared and x plus iy z minus r squared x okay, plus minus all right, yes. I need the minus. I just keep it. So then the next one, we know this one is this, therefore that is keep this. And this constant multiplied the left-hand side, right, so that is square root 16 pi over 5. And then 2 now, right? That is first term. Second term. Second term, let me first 3 over 2 half. So now I have this factor here. 8 pi over 15. Now inside, if it's x minus iy, that's plus. That is y minus 1, right? First one. Second one is minus x plus. So this is I put in fact. So this one, that's this one. This is x plus iy, but we need a negative sign. So here we have a negative y2 1, right? y2 1 is positive here, x plus iy, but we have a negative sign here. So I have a negative sign here. And plus, here, this is nothing but this one plus. So minus 1 is the plus, and x minus iy, right? So that is y2 minus 1. Now, let's reorganize the coefficient here. So this cancels this also, so square root 1 over 5, right? And this one, you see here, yes, you see here, this one is 5, right? 3 over 15 is 5. And here, this is a 4, right? 4, they become 2. And pi square, so that is square 2 over 5. And I move this positive in the first. So now I can rewrite this function as a linear combination of the several spherical functions, and the spherical harmonic are the eigenstates of L square and Lz. So now, once we have this, we can do following. That makes sense? Okay. So now let's do. This L square y0 plus L square on square 2 over 5 y2 minus 1 minus y2 1. Okay, then we apply this here, right? For any eigenstates of spherical harmonic, the L square apply this equal to the eigenvalue of the L square is h bar. So now that's equal to, I'm going to keep this constant. So when L square apply the y2 naught, when L equal to 2, right? Here L equal to 2, so that is h bar square 2 multiplied 2 plus 1. Here, right? And then multiply itself. And the second one, I keep the constant here. Then L square on this y, whatever ML is, always equal to, because L squared only depend on L, right? So you will have the same thing. H bar square 2 plus 1, y2 minus 1, and minus H bar square 2 plus 1, y2 1. That's it, because it's same L. L is equal to 2, right? So now finally, those are, you see, this is a 3 multiple 6, right? So, yes. So we have a 6 square root, okay, now so we have 6 h bar square, and inside is square 1 over 5 y2 0 plus square 2 over 5 y2 minus 1 minus y2 1, and that is 6 h bar square sine x squared theta. So what does it mean? That means when the L square apply this wave function, it gives us numbers multiply a function again. So that means this one is eigenstates of, is one of the eigenfunction or eigenstates of L squared, right? With the eigenvalue of 6 h bar squared. Or correspond to L equal to 2 case, right? So that is the first question. Second question, now we do the same thing since we already know this wave function can be written in linear combination of eigenstates of the LZ. So when LZ apply the states, it is LZ 1 over square root 1 over 5 minus 2 0 plus LZ over 5 minus 2 minus 1 minus 1 2 1. Now LZ here. LZ depends on ML. So different ML give a different. So just follow this. We have here. So we keep this coefficient square root 1 over 5. Then when this one 2 0 ML is 0, right? So that is h bar multiply 0 and the function itself. Right? Because here ML when y 2 0 ML is 0, right? So that is the number of the ML is 0. And plus second, this one square root 2 over 5 and inside h bar. First one, this one is ML is minus 1, right? And the second one is h bar multiply 1. ML is 1. Then this is 0, so the remaining I take h bar outside. So I have, and this minus is minus, and minus h bar square root 2 over 5. And inside is 2 minus 1 minus 2, 1. So that it is not equal to self. So this one is not the eigenstate of LZ because different ML. LZ is to be have the given ML, then we have a given eigenstate for LZ. But it is eigenstate of L squared since all L are same.
Shouldn't it be plus?
Yes. Okay, so we answer the second question. The third one is easier since we already have this one, right? Already have the L squared applied this wave function give us this. So the expectation value of L squared is equal to, that is here, I already used this result here, right? So that is 6 h bar squared you will see that equal to, let's look this one. Here. So you see here, this psi is linear combination of this plus this. Then you do the square with the inner product of this one is equal to the bra. So bra we have this one, right? So that one only the orthogonal. So only with this one the same. So that you have a square root 1 over 5 square. So that is 1 over 5. And another bra has same one. So only the same is non-zero, right? So we have this factor. And this one also this factor. So you will see it's equal to 1. You see here, because, okay, that makes sense? Do I need to write down again? Here, that equal to 1 is calculated, what it looks like. Okay, so is right, so 1/5 bra. Okay, this, yeah, I use bra, so that is why, because bra for you is easier to understand. Bra 2 minus 1 minus bra 1 multiply the cat plus so you see here, this one only non-zero is this term, right? So we have 1/5. And this one only for this one is non-zero, right? So we have 2/5. This one is minus plus, right? Right, so then the expectation value, the reason why here, because this denominator is 0, is 1. It's already normalized. If not normalized, you have this expectation value in general is this one, right? But now this one already equal to 1, so that equal to the denominator. If asked you to do this, you be careful first, double check this. Okay, so that is the first question. First question, I think I can do this. Let's see the second question. Second question is, okay, so I think I only need to remove this. So second question. Second question is L plus. And also the expectation value of this is the second question. Okay, so now let's continue. I think here, just remember L plus, okay, almost finished, right? You have this and you take square root is square root 6 and 5. So let's first, we know L plus applied is circle harmonic. It gives us always reaching by 1 unit, right? That is this one. L minus and L and L plus and L plus 1. L and L plus 1. Okay, we are going to use this one. So when L plus apply the function, so x y z is L plus, here we already write down here, right? So that is inside square root of 1/5, y20 plus square root 2/5, y2 minus 1 minus y2 1. Then we do this, apply this for each case, right? So then let's first the first term. Okay, so now this L is 2, M is 0, right? So now H bar square root, L is 2, M is 0, 2 plus 0 plus 1, right? That is the first one. And then M, L plus 1, so now from 2, 0 to 2, 1, right? Reaching 1. Then L plus apply this one. Is this, therefore this. Then second term, square root 2/5. Then here, okay, let's keep it. So inside here, this one is H bar square root L equal to M equal to minus 1, right? So minus plus 1. Minus L is minus 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 plus 1. 2 minus 1 plus 1, right? And then this y2 M L from minus 1 to 0, right? To 0. And then the next one is minus x bar square root 2 here, minus 1, m is 1. And L is 2 plus 1 plus 1, y 2, 2. Now let's do, so here, this one is 3 multiplied 2, so square root 6, right? Square root 6, 6 over 5, h bar by 2, 1. That is this one. And this one, keep this partition outside. Okay, I can put h bar here. So this one is 3, this one is 2, that is square root 6, right? This one is 1, this one is 4. So that is minus. Okay, if you want to write, make this coefficient final. H bar by 2, 1. And here, you can keep it or take outside. Let's see, I think that's correct. Yes, I keep that. Keep square 6. That's 0 minus. This is a 2, right? Okay. Now we are going to answer this second question. Since we have already know how to plus apply this function, then to calculate this expectation value of this inner product of this, we just do following. Bra, okay, bra. Okay, I use bra. So that is square root 1 over 5. Y 2, 0, right? Or 2 naught. 2 naught. And plus square root 2 over 5. Inside y 2 minus 1 minus y 2, 1. That's bra. Okay, multiply here. The right part already obtained here is this one, right? So that is square root 6 over 5 by 2, 1. And the plus square root 5 over square root 2 over 5. And inside is square root 6 by 2, 1, 2, 0. By 2, 0 minus 2 by 2, 2. Okay, now let's see here. Because this one,
Should there be an extra clue?
yes, and this one. So this one is this one, right? They are non-zero, so now you have square root 1, 5, and this one plus square root 12, right? H bar. So only this term non-zero, and then this one, there's no term, right, for the 2 minus 1, only this one. So this 2 is minus, this is minus, right? 5 multiply 6 h bar. And this one, no any, only this one, right? So no this term, so that's only these 2 terms. And they cancel each other, right? So that makes sense. I mean, makes sense in this case. This is, you know, this expectation value of the L plus in any states of any state is 0. So if even the linear combination also, but here of course is a minus sign. So this is a case that equal to 0. Okay, that is the second question. Third question. Number 3. They ask, how about if we measure the z? So if, okay, measurement. The z components. L orbital is carried. It is carried out. Okay, and finding the probability is finding the probability from the probabilities. So probabilities. Corresponding to the value correspond to the H0, H bar, and minus H bar. Understand the question? So now we are going to do the measurement. Measurement means LZ apply this, right? Remember at the chapter 3, one of the postulates, when this one is changed to another state, right? But if there is any state of linear combination of, then you will see what happened, right? So now, this is the question asked. So now, what you need to do is look this. Let's look, when they apply this, so we are going, that means we are going to measure the z components of L, so that is LZ. So when apply this states, what happened, that is here, I think I already do here, right? Already here. So I just write on this result here. Is minus square root of this one, right? H plus 2 over 5 minus 2 minus 1 plus 1, 2, 1. So the expectation value, if we do the average expectation value of this, you will see it is this one, it is minus H bar 2 over 5. Okay. Just this side multiply this. So only when here, this one, right? So I need this for any time. Okay. So you can see here when we do this this expectation value, that means this states multiply this one. And the y now 2 naught, there's no y 2 naught, so that's 0, right? And then this term is this one, square root 2 over 5. Another one is square root 2 over 5. So you have twice, right? Okay, there's a minus, there's a plus. This is a plus, right? So I have this plus. So this is a minus, so that is, the first one is this one. Let's see. The first one, yeah, this one multiplies, we have negative sign. Second one has negative sign, so that is plus, because we have negative sign here. So that is 0. Now, we're going to find the probability. The probability in general, I'm going to use probability with decrease down to for given ML, right? This is asked ML. This means ML value, right? 0 plus minus 1. Since LZ, when ML equal to 0, LZ value is 0. So you measure, if ML is 1, so you get this H bar. If ML equal to minus, so that is the probability 2, okay, ML. Why I use 2? Because here, the only L equal to 2, right? So then here we already know that is 1, right? So that is this value. Then let's do. Okay. I use this general formula, so now the first one for m L equal to 0 case, right? So I'm going to say 0. 0 is 2, 0. And 2, 0 is you use 5, 2, 0, right? And here, minus 1 minus 2. So only this non-zero is this term, right? That is 50%, 1 over 5. That is probability to find this. Similarly for m equal to 1, which is 1, which is 2, 1. Then only this one, so that is 2 over 5. Similarly, for minus 1, you have same thing.
If we were to get a question like this
Yes.
on the exam,
Uh-huh.
would you accept the fact that these are orthonormal bases, and so we can just solve it like we have before of just taking the square all the way across over the total magnitude, instead of having to go through all of these steps?
Yeah,
You just jump
yeah. If you know that, yes, you don't need to do the details. You have here, and you know, okay, find this one is this square. So that's all. Yeah, you can just say that. Yes.
So this 2, 0 state is the same as the y 2, 0 state?
Yeah, that means L equal to 2, M L equal to 0. Okay. Now the last one, number 4. Last one is the challenge, how to understand the question. Probability, okay, of finding the particle, at the position. This position is theta is 3 pi over 3. Phi is half pi. We think the or this solid angle inside is d theta is 0.03. D phi is also 0.03. How to answer this question? The probability to find particle is square root of this or known of the wave function, right? That is first. So the probability, okay, but it's in this range, so that is, let me first give. This does not ask the position x and y, z. It asks the angle. So what we need to do is first write this one in the spherical coordinates. This is x, y, z Cartesian coordinates, right? So you need to find this spherical coordinates. Spherical coordinates, that is first, because these questions ask our probability for given theta, angle, theta and phi, d theta, d phi. This is a question. So in order to find this, that means you are going to find this psi as a function of theta phi square and multiply this element of solid angle sine theta d theta phi. So if you know this, then the remaining part is just a simple math. That makes sense? So try to clearly understand the question asked us. If question asks what the position for given x, y, z, then you are going to use this one directly. But if asked the angle, so you need first to convert this wave function. So now we are going to write this here. Let's come back here. So we're familiar with this the spherical harmonic in the Cartesian coordinates and the spherical coordinates. Now, because here this in term x, y, z, we have, which is already have this, right? We already convert into this spherical. So we start from here. And then each one we have the spherical coordinates, the expression for spherical coordinates. This one is go to the table 5.2. 3 cosine square theta minus 1, not the first one. And then space here, the second term. Now, y2 minus 1 is square root 15 over 8 pi exponential minus alpha sine theta cosine theta plus the second minus. Okay, plus, because this is a minus, there's a minus, remember there's a minus sign, minus plus. Exponential I pi and sine theta cosine theta. Okay, so we keep this one, so this cancels the square root. Actually, 1 over 16 you take outside, but let's keep it. This still keep here. And the second one here, this 5, 15, they will have a 3, factor 3, and this 2 with this one is a 4, right? So 3 or 4. 3 over 4 pi. Inside, this one the same, so I take outside sine theta cosine theta, exponential, and 5 plus minus alpha this one. And that one we know is we can also write in terms of cosine, right? So now let's keep this one first term. Second term, this is a 2 cosine theta, right? Cosine phi, factor 2. So factor 2, this cancel. That is the square root 3 over pi sine theta cosine theta cosine phi. Okay, that is the function which we are going to use. Is here. So then now the probability, now we can do the probability when theta equal to 3 pi over 3. And phi equal to half pi and sine theta, right? Pi over 3 d theta d phi. You just multiply this one. Multiply this one number with 3 over 2, pi over 3 power 3, and this half pi. So the remaining details I just give you, let you do that. Then you will see here, because this one actually equal to 0. When phi equal to half, right? So that cosine half pi is 0. So this term disappears. Okay, just value is only becomes square root. You have a square root. Sorry. Ability is theta equal to pi over 3 and pi equal to pi over 2 plus sine pi over 3 d here, this already is 0.03 squared. Since we have given us this d theta equal to d phi is 0.03.
We don't have to fully integrate it.
No, this is just at this position with the volume, volume element here. You don't need to, because it just gave at this position with level, so you don't need this infinitesimal small volume. Or, yeah, just do it and give you the value. Very simple.
So where did the sine theta come from in this equation?
This is a d omega. Right, so that actually asks you the probability to find, this is something like this. Probability to find the particle in this small area with this is a d, right? And you have a theta. Here you have a phi. That is, what is the probability along that solid angle? Whatever the r is. So if within this solid angle, this direction, that is the question asked us to find the probability. Okay. Yeah, that is, now I want to do one more examples. So this one is quick, but a totally different idea. So we'll not do it like this. Example 2. So this one is find the energy level levels of particle which is free. Except that it is constrained to move on the surface of a sphere with the radius. Okay, this is a question. So now it's asked us energy. Here it gave us, asked us how the L square, Lz, and L plus minus applied states. And the key is we have to rewrite the states from the Cartesian coordinates to the spherical coordinates. Then the remaining part is just use what we learned. Now this one is listed here, a question like this. So we have a sphere with R, right? The surface. Then the particle is Y, X, Z. The particle is here, right? It can move free, but its free is only free on the surface. That's the constraint, right? With that constraint, so we are going to write down the Hamiltonian. First, Hamiltonian is kinetic energy plus potential energy, right? In general. So now, since it's say free, means no any potential, the only difference is the constraint on the surface. So that is only the kinetic energy, no potential energy, right? That is this Hamiltonian. First, to write down the Hamiltonian, then we are going to solve the eigenvalue problem to find energy level. So now, in this case, in spherical coordinates here, how to, if there is no strict constraint, don't we know that is a Lagrangian, right? That is partial square, partial x squared plus partial square, partial y squared plus partial square, partial z squared. But because we have this one, so now we are going to go due to the constraint, right? We are going to take into account this constraint So let's look at this, because if we look at this, we are going to find the relation between orbital angular momentum and linear momentum. So here, by definition, we know that is the cross product of position operator multiplied this linear momentum operator, right? And this is AB cross product, inner product with CD, remember? So that is equal to A with C, and B with D, minus A with D, right? And B with C. This, I think you know this, right? Just to remind you, if you know that we have A vector cross B multiplied with C vector cross B. Inner product must be A inner product C and B inner product B minus A inner product B. So now, here, this, let me first get out. So here, this is an R squared, right? This is a P squared. This one is 0. Because not here. P is always tangent to the surface, right? And R always perpendicular to the surface. So the inner product of this R to P is always perpendicular is 0. So that equal to this. Then you will find the relation, the direct relation between the P squared and L squared. So from here, P squared is equal to L squared over R squared. Then I'm going to substitute into here, into the Hamiltonian. So Hamiltonian, I rewrite Hamiltonian by considering the constraint. That is P squared 2m equal to L squared 2m R squared. Now I'm going to say 2I L squared. Here I is moment of inertia, right? Because R fixed, max fixed, so that is a fixed constant. Okay, so now you can see, can you do the following? Now the Hamiltonian is nothing but the direct relate to this orbital angular momentum L squared. So the next job is, okay, we're going to find energy, right? Energy is H we are going to solve this, right? We're going to solve this. Now we will solve this one because since the wave function R is vector in the space, in the spherical coordinates is this 3, right? Or R but R is constant. So that is only function of theta and phi. So this eigenvalue problem or time independent Schrodinger equation became H sine theta phi equal to energy sine. Then the remaining is simple since we know that is only associated with angular momentum in the spherical coordinates. We have L squared or 2I apply. That's equal because let's do this one, right? So now we are going to look at the left hand side. Left hand side. Okay. Left hand side. H, the Hamiltonian apply this wave function is equal to L squared over 2I apply the function. And we know we're going to solve the eigenvalue problem, right? So that is, that was 2I L squared. So this one, the eigen value problem is for L squared. We know this one, the eigenvalue problem for L squared. The value, if I use what, remember we use the eigenvalue, let's just say this. Eigenvalue of L squared multiply. Right, that is the eigenvalue problem. So we know the solution. For this solution, we will solve is eigenvalue equal to h bar square L plus 1, and the eigenstates. The solution for this is spherical harmonic function. The solution, right? We are going to solve the solution, and we already know the solution for L squared is this. So now we come to here. So when h, therefore, here. So we are going to find the eigenvalue problem for Hamiltonian is equivalent to the L squared 2I Now we are going to immediately use the relation of L squared. This one equal to here, right? Is equal to the eigenvalue L squared h bar squared L multiplied L plus 1 multiplied this one. So now we have the solution. Follow, right? So follow that is h bar squared L plus 1 over 2I. Here, energy is a function L, because for given L, we have one value. L from 0, 1, all the integer numbers, and then the eigenstates. From minus L plus 1 to L minus 1 to L, how many? 2L plus 1. That is, now we answer the question. What is the allowed energy level? If the particle move on the surface for given radius, that means constrained on moving on the surface. That allowed energy is a discrete value, and this discrete value depends on the L. L can select 0, 1, 2, all the integer numbers, so that will change. For given L, these states here, we have how many states? So given L, energy is will not change, but how many states? Give me there are how many? 2L plus 1, right? States. So what is the degeneracy? Of L is 2L plus 1. Right? So what that means here? When we have energy and this, just consider in the 3 dimension we have angular momentum L. the L quantized have the forgiving L will have several the components of L which depend on L's orientation, right? So how many orientation allowed to L plus 1? But for given L, energy is always fixed. That means for given energy, we have for 2 L plus 1 states. That states are associated with different orientation of the orbital momentum. Okay, so this is the second example. See how we apply this. Orbital angular momentum, which we learned in chapter 5. Now we go to chapter 6. So from chapter 4, actually in chapter 4 we discussed one dimension, right? One dimension, Now we are going to go to 3D. That means now the particle does not limit to move along the one direction. It moves in the whole space in the 3D. So how to deal with this system? Then we go to chapter 6, 3D problem. Now we consider problem is we still consider single particle. Then the multi-particle system we are going to discuss on from chapter 8. Single particle with spinless. We will not consider spin in this case. With spin, from chapter 7, we are going to consider. So that is the system we are going to consider. Now, the difference is now we are going from one dimension to the 3D dimension. Then in 3D, what's the difference? Okay. So, the goal, right? So, or the purpose. So, the time independent Schrödinger equation. In 3D, right? That is our goal. Then let's look at Hamiltonian. 1D and 3D difference is there. Hamiltonian is kinetic energy plus potential energy. In 1D, okay, let's just direct consider the position in the position representation, right? Position representation. Let's direct consider it. So 1D we know this is negative md squared dx squared plus vx, right? That is 1D. But 3D here. This one is becoming Laplacian operator, and potential is function. In general, let's just say maybe the vector, maybe the. So here is go to 3D. Here also go to 3D. So that's different, right? Now. So depend on in Cartesian, depend on, let's just depends on the symmetry.
Are we guaranteed that the potential will only be affected by?
Time, you mean, yes, we just consider independent time. Depend on time, we are going to go to chapter 10. We include the time perturbation. So we always consider Hamiltonian, the potential is still just a function of the position. Then we are going to deal with the system. So in that case, we can separate this time differential equation become two parts. One is the time factor, another is the time independent, right? So now, depend on symmetry, we either in the Cartesian. We can say that Cartesian coordinates if the potential has that symmetry easily to describe in terms of or express in terms of this Cartesian or in sphere. depend on this. So now let's start from the first case. If they depend on the, in the Cartesian, if we can write down the potential energy is easier to express in terms of the Cartesian, x, y, z, then how to deal with the 3D problem. Let's do this first, and then we go to the spherical. In Cartesian coordinates, we will deal with like a free particle moving without any potential or potential in the box, or potential like harmonic oscillator around x, y, z. So we'll do some of the example like this. Then we do the spherical, do some others. Okay. Before go to the Cartesian, the detailed system, let's discuss in general. Let's consider here. I answer the Paris question. If, okay, let's say, if this Hamiltonian does not depend on time explicitly, so we have the wave function in general is Rt, right? Can be separated. It's a spatial part product with spatial part and time part. Remember this? So this Schrödinger equation is can reduce to the two part, right? Remember. One is h bar f t equal to t. I think I'm doing this h. Here I have also energy, right? Remember this, and this one gives like a function is like exponential I e to h bar. Now here we're going to solve this. This is a challenge. That is the potential is potential like this. That's not depend on time this way. So now we are going to focus on this time independent. Right, this is time independent. Short equation. Or we call the equation, or we call the eigenvalue problem. Okay. So even now here, even the Hamiltonian can write in term of this x, y, z. Does not depend on time. But since I need the potential representation here, just a function. Here, if this is still difficult in general, right? In general, it's difficult. And even in one dimension, we only deal with some particular, right? So that is still not easily to solve, but we are going to consider this case. But if the way the potential can write or separate into the x components, y components, and z, that means if this potential is separable, then you will see the Hamiltonian can write, okay, let's go to this. First, Laplace we know, right? The minus x bar square over 2m partial square partial x square partial square partial y square partial z square, right? Plus vx, vy, and vz. Then I can write down also separate Hamiltonian in three parts. Since here this is only x components, right? Here, so hx is plus vx, and hy separate, right? Only the y components change is the y and z. So you can see that it became very easier to deal with since now each individual is one dimension, which we already saw in the one dimension. Okay, so then now we're going to solve this. In this case, this is the first if, right? If this case, the first result, the first one, the second one, the wave function can be written in the product. Since the Hamiltonian is separable, the wave function can also separate or written as a product of these three functions, right? That's second. Then third, the eigenvalue problem over time interdimensional equation, this term can be further separate. Okay. So separate this one. I think I can go quickly since we put it in here. So now we're going to do this, right? This is what we are going to solve. Then we are separate into here. This is hx plus hy plus hz x y z Okay, how can we separate this the time interdimensional equation into the different? Let's do this. For example, here, I'm going to hx x. Let me just do this. I think you will know that. We are going, I just divided this both sides. And in this case, since hx only applies to the x component, so the y, z can move and then cancel each other, right? Okay, so now you can see here, this is only function x, this is only function y and z, they add all together to be constant. What does it mean? I move this to the right-hand side. Minus hz. This b, because this is only function x, and the remaining function b also give us a right-hand side to be constant. I'm going to say ex. Then you have said this one equal to ex, all right? Hx x equal to ex. That is eigenstate or time interdimensional function for x components. Similarly, you can do say you move now. Now you consider this part. So then you move this term to the right hand side and this to the left hand side. So you can see this part equal to e minus ex is ey. Right? So then you can just ey. And then the z components is easy. So now you can see I have three individual eigenvalue problem here, and you can also b is ex plus. Okay. Here. All right. Well then, stop here. I think on Monday, I'm going to do some examples for this Cartesian coordinates case, like free particle collision box, and if the time allow me, and we can do the harmonic. But you will see, since we're familiar with one dimension, three-dimensional if a separate goal is very easy. The solution, you solve each individual eigenstates and multiply together, that is total eigenstate. And add all the eigenvalues together, that is total image. Okay. For the final exam, I remember we discussed is Monday, 1 p.m., right? Okay. December 12, 1 p.m. And December 5, 5th. That is final exam at home, right? This is in class. I'm going to post on Blackboard again to because previously I didn't get the time, right? So now I fix this 1 p.m. in the adult. Okay, the homework I'm going to grade it and turn on Monday, so you will have if you have some mistake or you have questions, you can discuss. And Monday is our last class. Yes.
The take-home exam is 20% and the in-class is 15.
No. Take home is 50%. In class, another 50%.
Oh, the syllabus online says that it's a total of 35%.
Oh, okay, that is different. Okay, now this, when I say, let's do this way. Homework, the midterm exam, and final exam, right? So this is a 30% total, total score. This is 35%. This is 35%. But each one is use point. Points for each one is 100. And when I say this 100, 50% of this 100 at home. So this is, and then 50% of this one, so the 50% of 35.
Okay.
That makes sense? Yes. Okay.
Do you have any idea about the number of questions?
Take home 3 and then in class 3, totally 6. Yeah. Let's see, 1, 2,
I can't tell you how happy I am when you said that. Because I mean, exactly the same.
Yeah. I was like, well, I mean, at this point, it is what it is.
I was like, it can't be right. It was too easy.
My problem with that question is that there was no middle ground of helpful online that wasn't, here's your homework problem that we did for you. And I'm like, no, help me, don't do it for me. There was either completely off topic, unhelpful, or exactly the problem. And they're like, here's all the steps. And I was like,
Well, I looked at it. I'm like, oh, a commutator. We've done a lot of commutator.
you
And I'm
And
like, it's
The
this.
also, yeah,
They
every momentum
equaled
is
0.
Frequently.
Dr. Lee, can I ask your advice about scheduling next semester?
yeah, you mean the content?
No, for different class.
You mean which one?
There's 2 courses that I'm considering in the materials science and engineering. 600 and 601.
You mean not our physics 6?
Yeah, there's
So
no
what's the name of this class? What is it called?
there's no electives in physics, so I have to take an elective.
Yeah, what's this topic on this?
So one is energy, science, and engineering. That's 600 with Dr. Sankara. And then the 601 is materials, science, and engineering.
oh, I forgot you used that camera.
But you only select one?
Oh, your
one of
energy
them,
on
right?
the,
Yeah, I only need one
Or the,
more.
Well,
Me,
I
I
mean, I
select
have multiple
second.
batteries, but like that one,
More like
Yeah.
material
It's-
is
yeah,
yeah, it burns
related to
through
your
space. Like,
research project.